guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about an important class of models which are called graphical models. And probably today we talked about a special kind of graphical models named Bayesian networks. Okay. We have seen that the probability theory is very important in machine learning. In other words, you could with product rule and sum rule, so we have seen and learned to probability rule, product rule, and sum rule, and we have seen that they are so useful, and we could actually analyze all of the probability models with just two of these rules, so even very complex models. So sometimes analysis of the probability distributions are more easy if we can represent them with some kind of actually we diagrammatize them, and so we could sometimes analyze them using diagrammatic representations of the probability distributions. So this could be quite useful, and so we call them probabilistic graphical models, or PGM. So we want to talk about probabilistic graphical models, or PGM, today. Okay, but what is the advantage, or what are the advantages of showing the probability distributions with some graphs? Actually, we talk about what is graph in a short, but for now you just could think of that as a representation of probability distributions. So the advantages of having some kind of visual representation of probability distributions are the first advantage is actually they are simple way to visualize the structure of probabilistic models. So we can visualize the structure of probabilistic models, and so they can be used to design new probabilistic models, and you can create new models with manipulating them. The second advantage is that they could give you some insights about some useful properties like conditional independence property, that we will see that it is so important to have such kind of property. And the third one is that we could actually factorize complex computations, and so do some of them implicitly, and so representing probability distributions with some kind of diagram could actually ease complex computations sometimes. Okay, don't worry if you are a little bit confused until now. We will talk about it in detail in a short. Okay, so the first question probably you asked is that what is a graph? We don't want to talk about the very detailed mathematical definition, but we just want to get some informal definition of graph. Okay, the graph is actually comprised nodes, so every graph has some nodes or vertices, and they are connected by links, or we call them edges, or sometimes arcs. In actually probabilistic graphical models, which we want to talk about them, each node represents a random variable. And so yeah, so we want to begin with Bayesian networks. They are also known as directed graphical models. So Bayesian networks, also known as directed graphical models, or DAG. Actually, they are some links that have some directions. So in the Bayesian networks, we can see some nodes. Let's see, this is a node and this is a node, and so we have a link. Let's say we have a link between them, and in Bayesian network these links have some directions. So it could be like this or like this. But after Bayesian networks, we will talk about Markov random fields, also known as undirected graphical models. They don't have this directional links in between nodes. So a directed graph or Bayesian networks are very useful when we want to express the causality of something. So when you want to say this is caused by B, so you could see let's say you want to say A is caused by B, so you could show that with Bayesian network with this directed link. So if you assume that A and B are random variables. But undirected graph or Markov random fields are better suited to expressing soft constraints between random variables. They are not very explicitly say that there are some kind of causality between the nodes, but there are some kind of they are expressing some kind of constraints between the nodes. Okay, now we want to focus on Bayesian networks. Let's say we have a joint distribution. It is P of A, B, and C. So we have a joint distribution. It could be discrete or continuous, or actually, so it could be discrete or continuous. No difference. And so, okay, if we use product rule, hopefully you remember that what is product rule. So you could actually expand it. So you could write it P of C given A and B times the joint distribution of P of A and B. And also you could factorize this term again by using product rule as P of B given A times probability distribution of A. And this is true for any distribution. We don't have any constraint until now on the distribution. Actually, we could show this with Bayesian networks and actually with a graph like this. So you have 3 random variables, so you have 3 nodes in here. Each node represents a random variable. Then you have in here, you should have all the joint distribution, and in here you will have P of C given A and B. So the node of C is conditioned on A, so you have a link from here and from here, from A and B. Both of them are in here, so we have a link from both of them to C. And also, if you see this term, we have P of B that is conditioned on A, so B is affected by A, so we have this. And we have P of A, and there is no link from this side to this side, and yeah, so that's it. That is the graphical represents of this joint distribution. And now we could actually extend this for k random variable. So let's say we have k random variable x1 to xk, and okay, using the product rule we could write them as P of xk conditioned on x1 to xk minus 1 to P of x2 conditioned on x1 times P of x1. Okay, so in this graph, actually if we plot this graph, you will see that each node having incoming links from all lower numbered. So if you have xk, for xk we have a link from x1, x2 to xk minus 1. So each node having incoming links from all lower numbered nodes. We have said that to this kind of graphs, fully connected graphs. So in this kind of graphs, we have a link between every pair of the nodes. So if you select a pair of 2 nodes in here, we have a link between each of them. But actually we will see that the absence of some links could represent some information about the class of distribution that the graph represents, and they are so much more interesting for us. For example, let's say we have something like this. the graph is we have x1, x2, x3, x4, 5, 6, and 7. Okay, and now let's say we have a link from x1 to x4 and x5. We have these links, and also we have these and these. Okay, now we could write the joint probability distributions as, so the joint distribution means that we want to write the p of x1 to x7 as, so in here we just have x1, and x1 is not caused by any other nodes. We don't have something to x1, so we have p of x1 in here. Then for x2 we also don't have any incoming link to that, and the same for x3. Then for x4 it is conditioned, and it is caused by x1, x2, and x3. So we have this link, and this link for x4. Then we will have for x5, we will have x1 and let's say we have a link from here and x3. Okay, and for x6 we have, it is caused by just x4, and for x7 it is conditioned by 5 and 4. So you probably got how to write the joint distribution. It is very simple. By just looking at the graph you could write the joint distribution of the graph. So we also could expand this for k variable and write the joint distribution instead of writing x1, x2, and to xk we represent them by vector x. We could write them as the product of k equal to 1 to number of variables of xk given pak. Oh, okay. What is pak? The pak means that the parents of xk. So what does the parent mean? In here, for example, for x5, x5 has two parents, x3 and x1, or x4 has three parents, x2, x1, and x3. So for you could write the joint distribution as the product of conditioned xk to the parents of the nodes xk. Okay. So actually we did some kind of factorization in here. Just note that in Bayesian networks we don't have cycle in this kind of graph, so you will not see something like this. In the Bayesian networks, or because this creates a cycle in here, and also something like this. We don't have cycle in Bayesian networks, so we don't have. Okay, now let's see an example. We want to see the polynomial regression. Actually, we want to see Bayesian polynomial regression. Okay. So for modeling this problem, we have the vector of coefficients that for our polynomial model. So we call those coefficients W. So it is a vector. And we have observed data as T. These are targets of, so we could show them as T1 to Tn transpose. And in addition to that, the model has some input data. We call them x1 to xn transpose, and we have, let's say we have noise variance of sigma squared, and also the precision of the Gaussian prior over W is alpha. So we talked about precision is actually means that the inverse of the variance. We call that the precision of the Gaussian distribution, and the prior of the W is actually a Gaussian. So we assume that the weights coefficients of the polynomial model have Gaussian distribution. Okay, so we could write the joint distribution of T and W as P of W times the product of n from 1 to n of Tn given W. So we could actually represent this. So this is a joint distribution of T and W. So in here we have a W, and we have T1, T2 to Tn, and they are caused by W. So we have some links. We face this kind of representation a lot, that we have similar random variables in here. So you could actually show it by a more compact way for representing this graph, as you have a W and you put all of these in a box. So in here you have Tn, and we actually call this a plate. So you have this n times. So instead of visualizing with this graph, you could actually represent it with a more compact way. Okay. Sometimes maybe it is useful to, in addition to the random variables, we also want to make the implicit parameters explicit. So in here we talked about our parameters, so we could write joint distribution based on our parameters x, which are the input data, alpha, which is the precision of Gaussian prior, and sigma squared, which is the noise variance of the input data. So we could write that as, so because alpha is related to the prior of the weights times the product of Tn conditioned on W, Xn, and sigma squared. So now we could actually show this graph with the parameters in this way. So when you have parameters, you could show them in graph with solid small circles. So for representing this joint distribution, you have Xn in here, you have Tn in here, you have sigma squared in here, you have W in here, and alpha in here, and we know that it is n times. Okay, so as you could see, now we have some parameters, x and alpha, sigma squared, which we showed them by solid small circles, and we have random variable Tn and W, which we showed them by actually these kind of circles in here. Okay, and so in here it is the W just conditioned on alpha, so we have just this link in here. The Tn is conditioned by W, X, and sigma squared, so we have these three links in here. Okay. So and another point is that we will see that we actually see some of the variables in a network. So for example, for our training data, we know some of the Tn, right? Because Tn's are the actually target values for the polynomial regression, so we observe some of them. We call them actually observed variables, because we observe them. But some of others we cannot observe them, like W. So we cannot observe W. We call them latent variable or hidden variables. We talk about them so much, and you could see that the idea behind variational autoencoders or autoencoders and even lots of neural networks are actually the latent variables or hidden variables. So now for showing the observed variables, we actually could shade these observed variables. So we represent the graph, this graph with something like this. So it means that we have observed variable in here, we have latent variable in here, we have some parameters in there, there, and there. So there you go. So you have the Bayesian network for disjoint distribution. But what is our goal? So our ultimate goal is to predict the output for new input x hat. So we have a new input and we want to know what is the output. So we wish to find the corresponding probability distribution for t hat conditioned on the observed data. So if you want to show what we want in the graph, we could actually show that in a graph with, so we have x and in here, so it is like this. Let's just complete the graph that we have in here. So let's erase this. Okay, so in here we have W, which we have a link to t hat from W, because t hat is caused by the weight vectors, because we make the predictions by the coefficients and based on the input data. So we have input data in here, and we have noise variance. Let's that affects both t hat and tn in here. So this is the graph of the mentioned problem. So we could write the distribution, the joint distribution, t hat, t, and w. So this is big T, means that all of the tn's. So conditioned on x hat, which is the new input and the training data, and alpha and sigma squared. So we could write it as the product of Tn conditioned on x and w and sigma squared, P of w conditioned alpha and P of t hat conditioned x hat, w, and sigma squared. So by looking just at the graph, you could say that, so this is the joint distribution. This term is related to this part of the graph. So you have Tn conditioned by Xn and sigma squared and W. So you have three links, so you have three condition in here, and then you have P of W conditioned and alpha. So this is related to this term, and this term P of t hat related to this part of the graph, which is conditioned on sigma squared and x hat and w. Okay, now from the sum rule, we could say that P of t hat conditioned on x hat, x, t, alpha, and sigma squared is proportional to the integration. So in here we used sum rule. So it is the integration of t hat T and W conditioned on x hat x alpha sigma squared dW. So actually in here we implicitly setting random variable in T to the specific values in the data set. So as you could see in here and here. Okay, now you could see that we obtained some terms to have some probability distribution on the output that we want to have. So this is our goal in machine learning. So this is the first part that we talked about that. There are some other notes that we talk about them in the next session. I think for this session it is enough to just have some kind of idea that what is Bayesian networks and getting some insights about how to represent the joint distributions and so on. Hope to enjoy from this session and see you in the next session. Bye.